Geothermal is 60 to 70%. You can see here right around 70% like we talked about. Solar capacity factor, even solar is the green one. So it ranges from 0 to about 30%, but on average it's something like 15 to 25%-ish capacity factor. So you put the solar system in, if it's rated at, if you put in a solar farm that's rated at 100 megawatts, you can plan on getting an average of 15 megawatts out of it for years. That's a pretty big difference. But there will be times when it's as high as 40 or 50 megawatts. So in the wintertime it won't be as high. So if you look at the renewable supply, solar is the little black box on the top there. And you can see that it was pretty trivial. And it's still, in terms of, this is, you can see it's still small, but it turns out that solar is right now and is projected to continue to be the most rapidly growing source of renewable power or power of any kind in the United States. So partly that's because it starts off, if you're starting off near zero, it's easy to double something. If you have a big install base, it's a lot harder to double something. So partly it's because it's so small, but it's not just because it's so small. So in terms of actual capacity, you can look where solar is adding. So this is this year, the commitments that people have made. So this goes all the way to the end of the year, even though we're still at this part of the year that people have plants that should come online. And you can see how the capacity additions are changing. And solar, in absolute terms, solar is a significant contributor to the new capacity that's coming online, electrical power generation. Not just as a percentage of a small number, but in terms of an actual amount. So in terms of, so this is capacity. So this is, in that example that we used before, this is the 100 megawatts. So if you build a 100 megawatts solar farm, that's 100 megawatts of capacity that's coming online. But only 15 to 20% of that usually actually comes online on average. So this is actual generation, and you can see the numbers are smaller, but still solar is the largest growing.
So are most of these solar farms, or does it include is a large portion of it like residential solar?
So they're both. So it turns out that the utility solar, which are the big solar farms, are the biggest part of it still. So there's kind of three categories of solar into three categories. Utility solar, commercial solar, which would be like on the tops of large buildings or parking structures and things like that, and then residential, mostly rooftops installations for residences. And it turns out residential installations have now exceeded commercial installations, but they're both small compared to utility installations. I think I've got a graph on it. So internationally, this looks at the growth of solar on an international scale. And that big pink bar that you see there is Europe, and that's dominated by Germany. So I think I mentioned to you before that Germany got really committed to this CO2 emissions reduction back in 2004, 2005. So Germany, which is one of the least likely places to install solar anywhere in the world, because it's frequently cloudy, it's considerably further north than we are here. And so it's nothing like putting solar in Arizona, where there are a few clouds, almost no rain, and lots of sunny days with direct sunlight, fairly far south. So they put a huge amount of solar energy. This is kind of the good and the bad things about this investment. So this is capacity, and you look how this capacity grew like this, and the analyses that people have done, they made a similar investment in wind, and actually even bigger in wind in absolute numbers. And the CO2 emissions from Germany have actually increased instead of decreased, partly because they closed several of their nuclear power plants. And Germany is one of the few places, in fact the only place I know of, although I'm not sure it's the only place, probably the only place in Western Europe, I'm not sure about the only place in Europe, that is building new coal-fired power plants, because they have to compensate for. So this just didn't contribute much. In fact, the capacity factor in Germany for solar energy is, I think, 10%, maybe a little less than 10%. And so so they paid an enormous amount of money for a relatively small amount of stuff. Remember that they did this in 2005. Here's the price histories. So if they did it in 2005, this is, I have one of these as a function of year. I guess the years are up here. So they were paying prices, so they commit, if they built them in 2005, then they would have been committing to the purchases in 2003 or 2002. So they were paying something like $1, 2, 3, 4, $5 dollars per watt for solar power then. And solar power is now a factor of 10 cheaper than that. So they pay 10 times as much, at least for the solar cells, as you would pay if you bought them today, and they got relatively nothing for them. So that sounds discouraging, and it is discouraging to a lot of very practical Germans. But on the other hand, it was that investment. So this is what created the industry that allowed the prices to do this. So Germany probably justifiably feels that their huge investment in solar power was a kind of a contribution to the world in reducing CO2 emissions, even if it didn't reduce CO2 emissions by a lot in Germany. So this is pretty important. So it's you know, you look at these numbers and it's easy to not appreciate what these numbers are. So if you just think of your own salary for a summer job or something like that, think what would happen if your salary changed by those factors. So what this says is that since 2009, there's the cost of electricity has fallen, the cost of solar cell, the cost of manufacturing a solar cell has fallen by 90%, so a factor of 10. So if your salary increased or decreased by a factor of 10 in that same time period, that would be a staggering change, right? So sometimes when you see these 90% numbers tossed around, it's easy to not appreciate just how real that number is. So if you were making this work, then that's a
what caused that cost to drop so much? And is it going to keep dropping?
It's and people think it will keep dropping. It can't. So this is just the cost of the solar cell, and so it used to be that the solar cell was the dominant cost of a solar installation. It's not anymore. So the cost of the solar panel itself is now, depending on whether you're doing this on a rooftop or for utility, it's somewhere between 20 and 40% of the cost of the whole project. And so if you got 100, so if it went to zero, you still have to do everything else. You still have to build the facility and all the other electrical connections and permitting, all the other stuff that aren't figured into that. That in terms of your house, that's most of the cost of your installation. The solar panels themselves are less than half of that cost. So making this is a great lesson for engineering, and that is, for a long time, solar researchers have been focused on trying to increase the efficiency of the solar cell. Solar cells are, best of class solar cells are on the order of 20, maybe in labs, maybe as high as 25 to 30% efficient. A solar cell that gets installed and used over its lifetime is on average probably 17% efficient, which by the way is more efficient than a plant is in terms of an organic plant, than a tree, for example, converting solar energy to work. But that's still relatively inefficient. But let's say it was 20% efficient. So even if I could make it 100% efficient, which by the way would not violate any laws of thermodynamics. So this is not a heat engine, so the thermodynamic limitations of a Carnot cycle don't apply to converting radiation to electricity. But even if I were able to make it 100% efficient, I would get a factor of 5 change in the cost. If I could make the cell 100% efficient without changing its manufacturing cost, then I could effectively drop the cost of the cell per unit of energy generated by a factor of 5. But I've dropped it by a factor of 100. And so the smart engineers said, working on the efficiency, so most of the things you have to do to increase the efficiency actually increase the cost, not decrease the cost. And the cost increases more than the efficiency compensates for it. And so rather than trying to make the cell more efficient, making the cell more efficient, let's just figure out how to manufacture it at a lower cost. And that's where all the savings have been. So solar cell efficiencies haven't improved significantly at all, but the solar cell costs have dropped dramatically because of savings in manufacturing costs. And those come in part from just having a market that's big enough that you can make big investments in something. So it's the same as, so I do most of my own work on my automobiles, and I know it takes me 2 or 3 times as long, or maybe 5 times as long to do anything on my car as it would take a knowledgeable mechanic to do the same thing. Because they're doing it all the time, right? And they know how to do it. And the combination of not having as sophisticated tools and not having as much knowledge or experience slows me way down. But if the only thing I did was replace hubs on my truck, for example, if I just did that day in and day out, I could get really good at it. I could make an assembly line type of a thing, and I could do that in a 10th or maybe a 50th of the time and the cost that it takes me to do it by myself. The same thing is true of manufacturing in general. So if every solar cell you make is kind of a master's or PhD project, that's really expensive. But if you get it to the point where you're manufacturing these in mass, then they can get really, really cheap. Your automobile is a good example of that. So to buy something as sophisticated as a modern automobile for $15,000 or $20,000 is just mind-boggling. So $15,000 or $20,000 wouldn't buy a pump in a lot of applications. And your automobile is just an incredibly capable, sophisticated piece of equipment. The only reason that they can be so cheap is because we make so many of them in a very competitive environment that they get to be really cheap. They may not seem cheap if you're buying the automobile. If you were to go to find, so you buy a mass, anybody know what a mass spectrometer costs these days? Probably none of you, have any of you used a mass spectrometer? Do you know what a mass spectrometer is? So a mass spectrometer is a fairly common piece of laboratory equipment, but they get built one at a time kind of thing. They're not built in mass like other things are. So a mass spectrometer measures the composition of stuff. A relatively simple thing to do. And it does it on a relatively simple basis, actually. The principles of how it operates are pretty simple. It costs for a typical laboratory grade mass spectrometer would cost $125,000. I'm sure if you were building 500,000 of them a year, you could probably get that cost down to $1,000 easily. So just in terms of what's in it, but you can't. You only build. Imagine what makes probably a few hundred of them a year. So creating the market will in many cases, but not all cases, drive the prices down. So, and that's some of you will maybe go into government policy. That's part of. What government policy at its best is saying, if we create this tax incentive, is it going to enable this kind of a reduction in the cost of renewable energy, or is it just going to end up going lining the pockets of a bunch of investors and not actually have any societal benefit? And it takes a lot of good insight and knowledge to be distinguished. Both of those happen pretty much all the time with policies. Some of them succeed, some of them don't. So let's see, we're generating a lot of solar. I want to get to residential is now more important than commercial. This is where most of the solar is generated in California, Arizona. California, partly because it has favorable sun, but mostly because it has very favorable state tax policies. Arizona, mostly because of sun. Nevada, Utah, you see is clear down at the bottom, but even better. This shows one of the major problems with solar, and that is you install solar power and you get solar energy during the day and not during night. And these are at the end of May, which are the peak solar generating. This is about the most solar you will ever generate from this station. So so this is in Germany. So in the wintertime, that will be the solar contribution will be close to zero all the time. And so these are the system module prices. So the amount of, this is in dollars per watt of, so when you talk, so solar cells generate DC power, not AC power. So part of, more expensive than you would think, part of the expense of putting a solar system together is the converter, which converts DC to AC, the inverter they call it, to AC power. So not only does it have to go through that conversion, that's not all that difficult. Your automobile does that all the time in the other direction. Your automobile generates AC power that charges your battery with DC power. So the alternator in your automobile does that, but it has to be perfectly synchronized with the grid. So tying it together with the grid and making it so that you can put that power into your home without causing a short with the grid is a lot of the costs. So you can see where the costs come from. The residential costs are up at the top. If you do the module itself is this much. The difference between this and that is the rest of the system costs. And so you can see the module cost has shrunk quite a bit. The balance of the system costs have changed. They've also dropped a little bit, but not nearly as much as the module costs. So this shows that same thing in a little more detail, where the yellow part is the balance of system costs for residential, commercial, and utility ground-mounted fixed access costs. And this was in 2014. So since then, the costs have still come down quite a bit. But in particular, so these are, what's that? Probably that looks like 60 cents, and they're now down around 40 cents per watt DC for residential solar panels, which is 10 years ago, and especially 30 years ago, if you told people the prices were going to get that low, they would have thought you were nuts. So that's Sahin.
Oh, I have one. So I thought about the tax credits. Is that only if you're generating power and putting it on the grid, or like, let's say you want to generate hydrogen in a big facility, if you put up solar there, would you also get that kind of tax credit?
So that's all in the details of the tax credit, but in general, it's usually for grid-generated power. So, but since you asked the question, think about the finances. So currently, this is a debate going on right now in the Provo City Council. In fact, City Council passed this ordinance. Mayor said he would veto it. Council rescinded the ordinance, and now they're talking about what to do. So so when you build your solar panel on your home in the residence, then if you get, I think residential electrical power costs in Provo are probably 11 cents per kilowatt hour. Does that sound about right? That's probably about what they are. So you're paying 11 cents per kilowatt hour to the power company for your bill. But of that 11 cents, probably only about 3 cents of it is the cost of generating the power. So the rest of it is building and maintaining the grid, sending out the bills, collecting the money, all the stuff that you have to do to make this all work. But if you put this solar panel on your house, you can avoid the 11 cent, the retail cost, the 11 cents per kilowatt hour. So you're getting the whole retail cost back. And in Utah, we are a net metering state, which means that if you generate more solar power than you need, you can put that on the grid and you get the retail cost of that also. So if I'm generating solar power on the grid of my home, I'm effectively getting 11 cents per kilowatt hour from the power company to do that. If I'm generating electrical power from a natural gas-fired power plant, I'm probably getting 2 or 3 cents per kilowatt hour to generate that electricity. And the people that build the solar panels on their homes aren't contributing anything toward the maintenance of the grid, which they need in order to be able to stay. They aren't contributing to the operation of the power company in terms of keeping it functioning and all of their overhead costs. And so many people say you shouldn't be getting that 11 cents. There should be a fee associated with connecting your solar power generator to the grid, so that you are also helping to pay for the grid and for all the operation of things. Other people say we already paid a lot for this solar panel. We are reducing CO2 and we are stabilizing the grid. We're decreasing the demand on other systems. We shouldn't have to pay additional money because this is already more expensive than just buying grid power. Why should we have to pay additional money just to be able to, for the rest of the society to benefit from what we're doing? And like many things in life, there isn't any clear right or wrong answer there, but those are the kind of policies that people debate. And most places are charging some sort of a fee to hook up to the grid for solar systems these days. That has a big impact on the value of your rooftop solar. All right, so I want to get into the science so we can talk about your homework a little. So this is just more installed costs are decreasing kind of stuff. So So if you look at the solar energy balance, we have 174 petawatts of electricity coming to the surface of the Earth. Significant amount of it gets reflected by the atmosphere, some is reflected by clouds, some is reflected by the Earth's surface. And we get 89 of those 174 actually absorbed by the land. And the Earth is warmer than space, and so a significant fraction of that radiates from, well, this is radiated from both the atmosphere and from Earth to space. This is heating up the air. This is what it takes to vaporize the water that eventually becomes rain. This is re-radiated to the atmosphere. It goes back into here to be radiated to space. And this is radiated directly from the Earth to space. And what we need to work with is what's left on the surface. So if you look at the surface intensity in terms of kilowatt hours per meter squared per day in the United States, this is how it looks. So here, there's too many clouds for it to be really high. Not very many clouds in this area, fairly high elevations. And so the southwest portion of the United States is the most premium place for solar power. If you remember when we talked about people, nobody lives here, in effect. All the people live back here. So, that's one of the problems with renewable energies in general, is the resources aren't very well. They don't correspond to where the people live very well. So let's get to the physics of how this works, because that's your homework. So we will come back to, so there's two ways you can use solar. You can use solar thermal power or concentrating solar. This is where you heat up water. You can either just heat up water and use the water to heat buildings, or you can heat it up a lot and generate steam from it and make electricity from it. That used to be, but is no longer, the cheapest way to make electricity from solar power. And a lot of people made huge investments in these solar towers, things that look like this, to try to harness solar energy by that mechanism. But now it's much less complicated. This is if you're driving down I-15 and just as you cross into Nevada, if you look up to the right, you can see these towers that are sitting out here in this desert. And usually they're really bright. If you go at nighttime, you can't see them, of course, because the sun's not shining. But if you go to the day, there's these they look like huge candles sitting out there in the desert, with a really bright top on them. And all of these are reflecting things that reflect the light up to there. That's the Ivanpah facility that Google and others invested in. And this is just kind of the risks you take with these things. So it turns out that it generates somewhere between a fourth and a third as much power as it was designed to generate. So it was way underperforming from what they thought it was going to do. And it's way more expensive than what they thought. So I think this is it. This shows you the details on it. I won't go through the details, but they're now petitioning the government to help pay them back for their investment here, because it didn't work out the way they thought. So people in the government have to decide whether poor and broke Google deserves a $540 million rebate for their investment or not, or if they're doing well enough. Google's only one of the investors.
What about it? Or like, where did they miscalculate the efficiency, or like, where did they go wrong?
So the quality of the sun has been less than what they predicted. That they should have known that quite well. The maintenance, there's not a lot of rain out there, but there's a lot of wind, and it blows dust around, and it gets on those mirrors, and so it's really high maintenance costs for keeping the mirrors clean so that you can get good reflection off the mirror. But candidly, I think it was a bunch of renewable energy enthusiasts being overly optimistic, and so that if you take kind of the best estimate of what's going to happen and do that all the way through a process, you end up with a factor of 2 or 3 higher prediction than what you should have done if you were being more realistic about how everything's going to perform.
So I know that they just petitioned like last year, the year before, to double their natural gas consumption as well. That's how they really send the power in. So do these things really like cut down on CO2, or is it all just kind of?
So they do cut down on CO2, but the real question to ask is how much are we paying for that reduction in CO2? And the answer to that in this case is there are way cheaper ways of reducing CO2 than this is. But they do reduce CO2, but not by nearly as much as they thought. Okay, so got to get to the point where we can get through your homework, all right? So photovoltaics are now the cheapest and much less complicated way of generating electricity from solar energy. So this is the energy distribution in terms of the amount of energy per micron. So this is like a probability density function. And this shows what a 6,000 Kelvin black body would look like. This blue line is what the radiation looks like at the outer edge of the atmosphere. The red line is what the radiation looks like at ground. Well, it's AM 1.5, so I guess I skipped over the AM thing. So the air mass ratio is the ratio of the distance from the outer edge of the atmosphere to the location you are, divided by the minimum distance right there. So the air mass ratio of 1 means the sun is directly overhead and your panel is facing directly to the sun. 1.5 would mean that this distance is 50% larger than that distance. So only near the equator can you ever get to a 1. And but if you get away from the equator, you can get to 1.5s, and it's a fairly typical air mass ratio. So the reason that it has these chunks in it is that this is water and CO2 and other things that are absorbing energy in the atmosphere at those wavelengths, and otherwise it's kind of black body-like. So so for your homework, what I'm having you do is, instead of using this complicated function, which you could do if you had to, so if you do a numerical integration and you had the tabular data for all of this, you could integrate that, but that was too complicated. So we're just going to use a Planck function, which is what these smooth lines look like, and I think we're using 5,500 Kelvin, if I remember, anyway, something like that in the homework. And we're going to say that the incoming radiation looks like that. And so I need to get to these diagrams, and then we'll talk about the rest of this. So this is how a photovoltaic cell works. So photovoltaic cells are semiconductors, which means that they conduct electrons fairly well, but not as well as a metal, but considerably better than a ceramic. And in a semiconductor, so in a metal, so in all materials there's a conduction band. There's a level at which the electrons are mobile enough that they can move they can move throughout the material they're not associated with any one nucleus. And that's called the valence band or the conduction band. And it's that's the conduction band. And in semiconductors, the conduction band is above the band where most of the electrons actually exist, in the valence band. So this is the outer valence electrons. In a metal, the conduction band is below that, so that the valence electrons are moving through the material without being associated with any one atom. This gap gets bigger and bigger. In a semiconductor, the gap is finite but not too large. So what happens is a photon comes from outside and excites one of these electrons and moves it into an excited state. And if that excited state is high enough that it gets into this conduction band, then that electron can now be conducted out of the system. It has higher energy, and you can conduct it out of the system. It can do work. It loses its energy by doing work, and put it back in the system, and it comes back in the valence band. But in order to get it out of the system, you need to create a potential that it will flow down. And so the PN junction that you put into any semiconductor is that potential. So what happens is the photon comes down here, strikes the electrons, puts a bunch of them up in here, and then by putting a charge across this, you can conduct those electrons out. And they also the electrons also create holes, and the hole, that is the place where electrons should have been in the valence structure. And those holes also they don't migrate because they're not in the conduction band, but when they come back, this will go out and do work, and when it comes back, we'll fill back in those holes and we'll come back up again. So overall process is photon hits the electron gets boosted to the conduction band, goes out of the photocell at that excited state. That's what generates the current that makes the electricity that drops its energy back in, comes back in, and that just happens over and over again. So if the photon doesn't have enough energy to get the electron all the way to the conduction band, then it just falls back down into here, and all of that energy just goes into heating up the solar cell. So the solar cell gets warmer, but you don't collect any electricity. If the photon has more energy than it takes to get to the conduction band, and it promotes the electron to this level, and then the electron collapses to the conduction band level, And all of that energy, the excess energy here, is the energy that also just gets converted to heat, and then it gets locked into this conduction band, and that's what generates the electricity. So in this electromagnetic spectrum, if we plot the Planck function versus, and you can do this either versus lambda or versus wavelength. Lambda is wavelength, or sometimes you see it plotted as a function of frequency or wave number. And in both cases, it looks like this. We'll talk next time about everything not the same. And I'm going to plot this way because it makes it a little easier to understand. So this is frequency. I'll just put frequency here. Energy scales directly with frequency, right? Photon energy is proportional to the frequency. So if the band gap is here, then all of this material is promoting electrons not high enough to cross the band gap, and so that forms no electricity. So all of the photon energy below the band gap frequency does nothing to contribute to electrical power generation. Okay, then the energy above the band gap frequency will generate electricity. Right here, you can, at least in theory, 100% of the energy from the photon gets converted into electricity, and you can produce electricity with 100% efficiency. But when you get to higher frequencies, now we are promoting electrons past the band gap, and the excess energy also just goes into generating heat. And so the efficiency, the amount of energy that you can generate, starts to look something, if you were to plot it out here, starts to look something like this. And the further out here you get it, so the further you go in energy, as you're way out here, then most of the energy is going into generating heat and just a little bit into electricity. And if you're closer, then most of it's going into electricity and a little bit into heat. And so have I gone through that too quickly? The clock is pushing me a little bit here. So. All right, so for your homework, what we want to do is to try to figure out the, so there are the two major losses in a photovoltaic cell are the losses that you get here where the energy is insufficient to promote the electrons to a band gap, to the band gap, over the band gap, and these losses that you get out here. And so I put a chart in your homework that shows there are other losses on there too, but they're smaller than those losses. And what we want to do is to generate a chart that shows how the efficiency of the full solar cell changes as we change the band gap frequency. To do that requires an integration which I would recommend that you do numerically. I put the analytical solution in there, but it's not very useful. It's an infinite series solution. So we just use a numerical integrator and a couple of things to represent. So what you want to do is to calculate the power that you're going to produce. It's going to be the integral of the Planck function, which is how much energy there is per unit wavelength, times, this is the important part. So the Planck function is a function of, and you can do this either with wavelength or frequency, and temperature. The lambda, and you integrate from 0 to infinity, and divide that. Efficiency is going to be that divided by integral from 0 to infinity of just the Planck function. So what goes in here is something that describes this curve. So that's going to be, so talk me through it. How are we going to describe that? So from here to there, it should be easy, right? How much, what fraction of the energy are we converting to electricity from here to there? 0, right? So this is going to be 0 for frequency 0 less than frequency less than band gap frequency, all right? And then what's it going to be from that point on? I think I gave you the Planck function in frequency, not the wavelength.
Yeah.
You can write it both ways. So all of this is stuff you know how to do, but you might not know how to do it. So there's some hints that are pretty helpful here. But think about what fraction of the energy are we going to produce as electricity past the band gap? just need a function in here that says what fraction of this energy is going into electricity. And so, can you see that if I put, band gap frequency over the actual frequency, well, and if I do that from band gap, frequency is band gap, less than that, less than that. So the total energy of the photon scales with the frequency, right? So let's say the frequency is twice as big as the band gap, then think through that before you look at the math, and half of that energy will go into making electricity and the other half will be lost in thermal losses, right? So if I put this function in here and the band gap frequency is here, this is going to be twice that much, I get 1/2 here. If this is 25% bigger than that, then I get the right number. For the same, I get 100% efficiency. And the limit of frequency going to infinity, this goes to 0 again. So to do this integration, you're probably going to want to use a numerical integration in MathCAD or whatever program you use. And let me just warn you that 0 to infinity, integrating from 0 to infinity means you have to find some number. Infinity is not going to work because your numerical integrator will take too big of steps and it will step right over this whole thing. So it'll integrate from here, and its next integration step will be there, and you'll miss all the structure. So you need to find some number that is effectively affinity, meaning the way to find it is you decrease this number until you get a stable answer here that doesn't depend on what that number is. So this number should be way bigger than the band gap frequency, but way smaller than infinity. So, you can do the numerical integration that way. Does that make sense? So I think the hints are pretty helpful to step you through that. And so we'll work through that for our homework. We'll talk about it some more. Sorry for running over.